Unit number is unit 4. Okay, so we are discussing about how to initialize the weights. So because if we initialize all weights to 0, this result in same H11 and H12. This results in same value of weights. Del W1 1 will be same as del W21. So new weight values are same. Similarly, instead of initializing to 0, if we start with same initial weight values, if W11 it's same as W12, if it is same as W21, and if it is same as W22, then all weight values are same, and hence your change in weight will be same, and all weights will progress in the same direction, or they are updated by same amount. Okay, so it won't be useful to achieve your desired output. Okay, so to avoid this, now we are considering third case, that is, say we are considering how to assign weights. Okay, so here we are considering a deep neural network with multiple layers. So here in input node, there are n nodes x1 to xn, and equivalently, we are considering same nodes at every hidden layer. So let us see, say S11 is nothing but summation I runs from 1 to n W1I into xi. Okay, so your variance for S11 will be given by variance of this term. So the same can be represented as summation I runs from 1 to n, expectation of W1I square into variance xi plus expectation of xi square into variance W1I plus variance of xi into variance of W1I. Okay. So we have used this simply by property variance A into B is given by expectation of A into variance B plus expectation of B into variance A plus variance A into variance B. Now, if we assume that all the weights and all the inputs, if they have 0 mean, in that case, expectation W1I will be 0. Similarly, expectation xi will be 0 because we have assumption that all weights and all inputs are 0 mean. Okay. So first two terms will vanish and there will be only last term. So your variance of S11 will be variance of xi into variance of W1i. Okay. So all inputs and all weights have same variance. So if we consider that all these inputs and all the weights, all of them are having same variance, then this will result in simply n multiplied by variance W into variance x. Okay. So your variance Si will be simply n into variance W into variance x. Okay. Now, if n into variance W, if it is very, very greater than 1, what will happen? Variance of S1I will be very large. And if n into variance W is very, very small, if it tends to 0, then variance S1I will be very small. So now let us consider what will happen at next stage. See, this is your next layer. So your output from S1 layer will be used as input to S2 layer. Okay. So here your variance at next layer S2 will be summation I runs from 1 to n variance S1 into variance W2. Now variance S1 is nothing but n into variance W into n into variance W1 and so on. Okay. So into variance X. So here S21 is directly proportional to n into variance W square into variance X. Okay. So assuming weights across all layers have the same variance. Here we have assumed that across all layers, this variance value is same. So we are simply multiplying it by n. Now, as we move to next and next layer, at kth layer, what will effectively we get is variance at layer k is n into variance w raised to k into variance x. Okay, so k represents particular layer number. So thus to ensure that variance in the output of any layer does not blow up or shrink, what we expect this n into variance w should be equal to 1. So in order to initialize weights, we take into account this condition. N into variance w should be equal to 1. If it is very large, your variance will be very high. If it is too small, variance will be very small. So to avoid that, n into variance w should be equal to 1. So thus to ensure that variance in the output of any layer does not blow up or shrink, we want n into variance w to be equal to 1. And thus we can try to initialize the weights from a distribution where this condition is satisfied. Okay. So here, so let z is a random variable from normal distribution or Gaussian distribution. So z is n01. So if 1 represents variance and 0 is 0 mean. So in order to achieve this, we consider normal distribution with variance 1, and we want n into variance w as 1. So we draw the weights from unit Gaussian distribution and we scale them by 1 by root n because we want to cancel this n so that we get n into variance w as 1. Okay. So we take variance of z by root n, and this n represents number of neurons in particular layer. Okay. So this results in initial weight values. Okay. So we use a normal distribution and we divide each parameter by square root of n. Okay. So that this we can achieve this condition n into variance w is equal to 1. Okay. So here when we use z by, we scale every weight by root n, we get this term, and this condition n into variance w is equal to 1 is satisfied. Okay. So we initialize weights to random numbers which are drawn from unit Gaussian distribution, and this is scaled by 1 by root n. Okay. So this avoids saturated neurons or dead neurons. Okay. So this works well for sigmoidal or Banach function, but it won't work well for ReLU. If we are using ReLU activation function, this won't work well, but for ReLU activation, we scale it by n by 2. Instead of square root, we scale it by n by 2. Okay. So this is about weight initialization. Okay. Now let us have a look at another problem, that is overfitting. Okay. So let us see what is overfitting. We have actually studied what is meaning of overfitting. So can anybody tell me what is overfitting or underfitting in case of machine learning? What is meaning of overfitting? Please type your answer in the chat box. What is overfitting and underfitting in general with respect to machine learning? Please type your answer in the chat box. What is overfitting? So when you have very few number of training samples as compared to your features, there is possibility of overfitting. So overfitting basically overfits your training model, and you can get almost zero accuracy for the training data. but that because of overfitting, that model won't give you good accuracy for the test data. So generalization won't take place, and the same problem can occur when we are talking about deep neural networks. Okay, so basically, deep neural network contains large non-linear neurons, and it tries to learn complicated relationship between input and output. Many times, sufficient training data is not available, and in that case, your network will overfit. Okay, so you have many number of neurons or parameters and insufficient amount of data. So in order to avoid overfitting, we can use various techniques like regularization or weight sharing. And one of the techniques is dropout architecture. So what do you mean by this dropout? Okay, so dropout refers to dropping out units. So as the name indicates, from the given deep neural network, we drop certain neurons from certain layers randomly while training the network. So for any particular training phase, number of parameters will be reduced, because when we drop certain nodes, we won't be considering weight values incoming or outgoing from those nodes. So your total number of parameters will be reduced, and it will result in avoiding overfitting. Okay. So this is basic concept behind dropout. So dropout means uh, temporarily remove a node and all its incoming and outgoing connections, resulting in a thin network. So as shown here, this is your original network where all the nodes are connected to all the nodes from next layer. But in case of dropout, here you can observe we have removed one of the input nodes. Then in second hidden layer, we have removed 3 nodes. In third layer, we have removed 2 nodes. And similarly, if you have more than 2 hidden layers, we can go on removing nodes from all the layers. Okay. So usually, while applying dropout, we remove 50% of the nodes from hidden layer, and from input layers, we are removing only 20 to 25% of the nodes. Okay. So how we apply the dropout process? So we initialize all the weights of the network and then start training. So for first training instance, we use a mini batch and we apply dropout, resulting in the thin network. So instead of using all training samples, we use few of the training samples in the first instance. Then we compute the loss and backpropagate it, and only parameters for the nodes which are active are updated. So the parameters which are related to dropped nodes, those are not updated. Okay. So for the second training instance, that is second mini batch, we again apply dropout, resulting in a different thin network. So for next instance, we remove few other nodes, okay, and then we repeat the process. So we compute the loss and backpropagate to active weights, and we continue the process. We can use multiple instances, and for every instance, we use different neural network architecture. We drop out different nodes. Okay. So this is dropout process. So with this technique, actually, we are training different neural network architecture with different subsets of input data. So weight matrix is same throughout the training. At every instance, we are updating different set of weights and not touching the weights of inactive nodes or dropped nodes for that instance. Okay. So the weights for nodes present for the 2 instances will be updated twice. There is possibility that some of the nodes are retained for multiple instances, okay? Because these dropping out is done randomly. So there are certain nodes which are present for multiple instances, okay? So the overall weights are getting updated multiple times as the same node is present in multiple instances of training. Thus, each thin network gets trained rarely, and sometimes certain nodes are not at all used for while training. But the parameter sharing ensures that no model has untrained or poorly trained. Okay. So here for different instances, we are using different nodes. So this is, it will look something like this. So we have picked a mini batch and we have from this network for certain batch, we have dropped certain nodes. So say these two nodes are dropped from this layer and these two nodes are dropped from this layer. Okay. So every time we are dropping P% of the nodes. Okay. Then for next instance, we are dropping some different parameters. So for this instance, we have dropped these two nodes and these two nodes. So effectively, your network will look something like this because we are not considering the incoming and outgoing connections from these dropped nodes. So effectively, your network architecture will be as shown here. Okay. So structure of the network is changed. Okay. So this is thinner than the original network. Okay. So we can train this particular network with first mini batch or first set of training samples. So for each mini batch, we resample the dropped out neurons. So we drop out different neurons for the next batch. Okay. So it is impossible to aggregate the 2 raised to n thin networks during testing, right? So for every training phase, we are using some different thin network. So what to do at test time? So at test time, we use the full neural network and scale the output of each node by the fraction of times it was on during training. So if a node is present with probability of 1 minus p during training, then all the final weights associated with it are scaled by factor 1 minus p because it has participated 1 minus p times during training. Okay. So this is during testing, we use the complete network as shown here. There is no dropout during testing, but if the dropout rate at training is p%, all the weight they are scaled by 1 minus p. Okay, so assume that the dropout rate is 50%. So if dropout rate is 50%, then all the weights which are participating multiple times or p times or 50% times, they are scaled by 0.5. Okay. So what dropout essentially does? Basically, it prevents neurons becoming lazy. If no dropout, output of a node affected by all the neurons in the previous layer. Thus, current node is dependent on other nodes and it need not be alert. But with dropout, this is not the case. Each of them have to be very careful. And thus, dropout does not allow nodes to co-adapt. Essentially, hidden units cannot rely too much on other units as they may get dropped out anytime. So each hidden unit has to learn to be more robust to these random outputs, to random dropouts. Okay. So dropout. So when teams up, if everyone expect the partner will do the work, nothing will be done finally. So say if you are working in a group and if you assume that your partner will do the work and you need not work, in that case, you won't be alert, right? And there is possibility that no one will work assuming that everyone else is working, and finally there won't be any output. Okay, so similar, but if you know that your partner won't be available, in that case you have to be alert and you have to complete the work. Okay, so the same concept we are using here while dropping out certain nodes. Okay, so if your partner drop out, in that case you will do better, you need to work more, you need to work better. Okay, so every neuron is alert whenever we are applying dropout. Okay, so when testing no one drop out actually, so obtaining good results, eventually we will get good returns, because during testing we are considering all the nodes. So why we multiply the weights by 1 minus p while testing? Because training of dropout, certain nodes are participating multiple times. Okay, so during testing there is no dropout. So if we use the weights as it is, actually we will get the output 2 times required. Okay, so to avoid this, we multiply all the weights by 0.5 and then we will get the expected result. Okay. So now we will talk more about dropout and other issues related to deep neural networks in the next lecture. Now I request all of you uh, uh, to type your attendance and please don't leave. I like to discuss about your groups. Okay, so please wait, type your attendance and wait for your groups and about group activity. Okay. Now I'm once again sharing the screen so that you can check your groups. So these are the groups and topics are written in front of you. So here, okay, so these are the groups. There is some small modification because few of the students they formed their group earlier. Okay, so there is only question of this Jain Palash and Ashish Kumar Pal. So I can add both of them to group number 6 and I will reshare.
Ma'am, Ma'am Palash is there. Ma'am Palash.
Okay.
I have also created the group with Akshat Pote and Chaitanya Rani and Bhaskar Jha.
Where are these students right now?
Ma'am, group 6 only. Group 6 only.
Only, na? So 2 of you will be there in group 6. Okay.
Okay, ma'am.
Okay. So I have given you topics as shown here. It is written here. Okay, so now start working with your group. You have to review number of papers which are equal to the participants in the group. So if there are 5 students, you have to review at least 5 papers. You can review more than that on the given topic, and you have to present your work in front of the class, and some other group along with me will assess you. Okay, and this is your second assignment, which is a group activity. And from next week, we will be starting with presentations of the group one by one. Okay, so I will let you know who will present in next week and during which lecture. And in every lecture, there will be 4 groups. Okay. Okay, so Rajanandini, okay, so you tell me which topic you are interested in. Okay, kindly convey me. Okay.
Okay, ma'am. Yes.
ठीक है. Okay.
Ma'am, do we tell you now or later on?
Later on, as soon as you find,
Okay.
you please let me know.
Okay, ma'am. We'll message you.
Excuse me, ma'am. So now I am in group 6 now.
Who is this?
Palash.
Yes, yes, you are in group 6. Okay.
Okay, ma'am.
Okay. So that's all for today. Okay, thank you all. If you are typed your attendance, you can leave the meeting. Thank you all.